Hello everyone and welcome back. This is the first lecture and we shall be talking about the appearance of early mathematical discoveries. So the first math developments that we shall mention are the ones of Egyptian civilization. Emphasis during that time was certainly on the practical side of mathematics, and that is because mathematics, it was seen as a facilitator of trade, agriculture, and other aspects of life. Records actually indicate that by 2000 BC, Egyptians had a primitive numeral system, as well as some geometric ideas about, let's say, triangles, pyramids, etc. As you can see, I have written here, the first example relates to figure 1, and I shall explain what that is. Egyptians had a way of actually building a right triangle. So here's what they did. They actually took 12 pieces of string, or let's say string equally divided among one another. There are 12 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And to create a right triangle, what they did is they took the 5 of those and they placed them on a straight line, let's say from point A to point B. So 5 of those, 1, 2, 3, 4, 5, were placed in a straight line, and then once they had this straight line, that would pull the remainder, and they will pin it somewhere, and the result would have been a right triangle. Obviously, this is a right triangle with 3, 4, and 5, which is actually a very familiar object. It's actually known as the Pythagorean triple for a right triangle. Now, so this gives us a glimpse of, actually it's not an application of the Pythagorean theorem, but it is rather the converse of the Pythagorean theorem. So they knew that should we have the square of the larger size being equal to the sum of the squares of the sides, the resulting would have been a right angle. Pythagorean theorem, as we all know, says that in a right triangle, the sum of the square of the hypotenuse should be equal to the sum of the square of the sides. Here you have 1, 2, 3, so this is 3, this is 4, and this is 5, and as you all know, 3 squared plus 4 squared indeed equals 5 squared. So they knew this property of the right triangle, so they knew how to build a right triangle, but it is certainly not clear as to whether they had a proof as to why this works. So during that time, we had the whys, we had the hows, but not the whys. So the notion of proving a general mathematical result by logical arguments is nowhere actually to be found in early Egyptian writings. Here's another example from the time. Example 2, it refers to figure 2. I'll explain what that is. Basically, this is a truncated pyramid. I say square pyramid because we mean a pyramid with a square base. So we have a truncated pyramid. Truncated means that the top is cut by a parallel plane with the base. So Egyptians again had a recipe for describing how to find the volume of this particular truncated pyramid. A pyramid with base being a square of size 4 and the top one is a square of size, not size 2, but the length of the side is 2, and the height is 6. So this recipe tells you exactly how to get the volume of this truncated square pyramid. It says square 4 resulting in 16, double 4 resulting in 8, square 2 resulting in 4, and then add the 16, the 8, and the 4 in resulting 28. After, we shall take the 1/3 of 6 resulting in 2. Finally, we take 28 from here twice, resulting in 56. And as the legend has it, it says, see, it is 56. You'll find it right. This is actually taken from the so-called Moscow papyrus from 1850 BC. It has actually nothing to do with Moscow per se. It is actually an ancient papyrus owned by the Egyptologist Vladimir Goknichev, and it was purchased around 1892 or 18